Hello everyone and welcome back to this course on discrete mathematics. And today we are going to deal with graph theory. In mathematics, graph theory deals with graphs. And of course, we have touched a little bit of graph theory in some of the parts earlier, but today we are going to look into the very basics of the graph theory. And of course, the applications of graph theory is quite wide. It's especially in the field of computer science. So you could say that graph theory, they can develop a relationship, or you can actually model a real world system into a graph theory more easily. So while we talked about relations, we did discuss how that can be expressed by means of graph theory. Now likewise, there are a lot of other places where we use graph theory, and today even for routing problems, even like the shortest path or the efficient way of merging circuits, even the so-called integrated circuits. Apart from that, a lot of other applications, even for designing the smart urban infrastructure like smart cities, people are using graph theory. Let's go and see how things are possible and how the graph theory evolved. This is one of the famous problem that people started with when they consider this graph theory, the Severn Bridge of Koenigsberg. So as you can see here, this small town of Koenigsberg has been connected by means of 7 bridges. The question is it possible to walk with a route that crosses each bridge exactly once? That's quite a tricky question. So people started to come up with their argument. In the meantime, as you can see, this as a town, and in order to model this problem into a graph, 2 or 3 simple steps are involved. For example, you just consider this as a map and remove the unimportant detail, or forget the unimportant detail, because right now while modeling this system, we are not worried about the things inside those town. For example, there might be buildings or even the streets or roads. And at times when we talked about relations and other stuff, we had an example where in fact we designed a system in which we consider the roads as edges, but here we are skipping it because our focus is on the bridge. Well, now we forgot the unimportant details and we come up with this diagram where it has 7 bridges across this river that passes through the Koenigsberg. And furthermore, if you want to further refine it, we can consider more, try to forget more unimportant details. That's where the actual graph comes in. As you can see here, all of these 7 bridges are being termed as 7 edges, or it's been marked as by means of 7 lines there in the black color. So that's the idea, trying to model a system into a graph. Right now what we did is that we in fact modeled this 7 bridges of Koenigsberg into a simple graph. Let's go further and let's define various parts of the graph before we go on to another properties of graph. So all these blue color dots, or you can call it as the nodes or the points or the vertices, we call them as vertex, and if you want to call as multiple vertices, called as vertices. Generally in our course we use the term vertex or a node, just for your reminder. and different books use different notations. Mostly they use node or vertex. Then right now we have 4 nodes A, B, C, D, and these 4 nodes are connected by means of this 7 lines. From the previous model we can say that these are the 7 bridges. So these lines are called the edges or edge. So in our course we are going to use the term edge to refer to these lines. How many edges are there? There are 7 edges. So here is the name: E1, E2, E3, E4, E5, E6, E7. So in general, while we refer a graph, we have to consider whether we would be able to solve a particular problem. So the question is again, can we able to solve the 7 bridge of Koenigsberg problem now? Do you remember what is the problem? Just to get back this problem there. Yeah, is it possible to walk with a route that crosses each bridge exactly once? That is the problem there. What do you think? Is it possible? Well, in fact, to find a walk that visit each bridge exactly, we can think of this question: is it possible to find a walk that visit each edge exactly? Because we have converted this into an edge problem right now. Try to find, is it? Suppose there is such a walk, there is a starting point and an end point. Say you start from A and you go through E6, then E5, say for example, E4, E2, E3, E1, and you are going to miss E7, because if you really want E7 you have to go through E2 again. Something is missing there. For every intermediate point V, there must be a same number of incoming and outgoing edges. So V must be an even number of edges. So let's start here. V must be this point that is coming in, and coming out should be the same number. So one that is coming in, one that is going out. Coming in, going out. But in our case we had 7 edges, which means there should be a point at which we could say that there may be some issues in coming in and going out. So at most 2 vertices can have an odd number of edges. So in this graph every vertex has only an odd number of edges. So there is no walk which visit each edge exactly 1. So if you consider closely, each edge has odd number. For example, each vertex A for example has 5 edges, vertex C has 3 edges, vertex D has 3, vertex B has 3. So with this considerations, you can't have a walk that we are interested in. Again, this problem of unsolved questions of 7 bridge of Koenigsberg, when it is possible to walk that visit every edge exactly 1. Let's consider this case where you have this 5 colored circle. Let's consider the edges and vertices as we have seen earlier, and let's try to find, is it always possible to find a walk if there is at most 2 vertices with odd number of edges? Let's see. No. As we have seen in the previous instance, it's not possible for us to find a walk if there is at most 2 vertices with odd number of edges. So let us consider this case. Is it possible to find a walk if the graph is connected and there are at most 2 vertices with odd number of edges? Yes, if it is connected, then we can consider that part. Let us talk about this more. So this walk that we are considering here is called the Euler's path. So we have this Euler's solution here. Let us talk about this Euler's theorem. A graph has an Eulerian path if and only if it is connected and it has at most 2 vertices with an odd number of edges. So this theorem is been proved in 1736 and was regarded as a starting point of graph theory. With this starting point, let us focus more on the actual graphs itself. Yes, there are types of graph, different ways to express the graph, and we do have different types in general. We have connected graphs, we have simple graph, we do have a balanced graph, we have graphs, we call it as directed graph, undirected graphs, a lot of different ways to express it. Let us talk with the first one is the simple graph, and this is undirected. So when I say undirected, I mean that it does not have an arrow. So that is the simple graph, and mostly we will deal with the simple graph throughout this course, and we will try to find various solutions for the problems and algorithms that we have using a simple graph. You have a multigraph, and often, as I told you, we do not deal with multigraph, and there is a type of graph which is called a directed graph. If you recall what we have seen in the relations, there we talked about the multigraph. In fact, we talked about the directed graph, if you recall about those things. And again, talking about these, I think we have skipped it. Okay. Again, talking about these graphs, if you recall the so-called relations, we talked about 6 degrees of separation. Even there, when we talk about social connections, this whole connections can be easily established by means of graph, considering one node as a person who is connected to another node. So that is another person. When a person is connected to another person, it is like 2 nodes are connected to each other. So in the same fashion, you can actually establish many more connections, whether it is a word. For example, the word geography is connected to, say, landmass or landscape, or even you could say arid land, valleys, mountains, of course even countries, rivers, a lot of other stuff are connected, but as you can see, the relation in which they are connected, it goes at different degree. Yes, when I say different degree, I mean the first connection has stronger degree in which it is connected, the second one has weaker and weaker, and so on. Well, in this course, as I mentioned earlier, we are going to just deal with the simple graph. So let us define this simple graph. It is quite important for us to understand fully about the whole graph informations. So in common, we just relate this graph as an ordered pair of G equals VE, where the graph G is represented by means of vertices and the edges. So this comprises a set of vertices. So that is why we call it kind of a G that comprises of the set of vertices or nodes or points that we have seen, along with that of set of edges or the lines or arc. So we in general consider these, for example, you can consider this graph that you have here, in which we can find there are 6 vertices there. Generally speaking, again, we are going to talk about this undirected graph, and this graph that is here is also undirected. The set of vertices we generally refer by V, and set of undirected edges we refer by means of E. So in other sense, the graph stems from the concept of edge set. We talked about sets in the past. So in one or more general notions, a vertex is a set together with relations of indices that associate with such edges that has connecting two vertices. Yes, there are a lot of general forms and notations in which the graph is being established. So V of G, where the vertex, we can see it's represented by means A, B, C, D, E, F. Yes, these are the vertices of this given graph. And the edges, E of G is AB, AF, BD, BE, CD, CE, DF. Right. So we can see V and E are usually taken to be finite. That's one of the general case, and many of us well know the results of these results is not true for certain applications or certain values, because for infinite graph there are a lot of arguments that would fail for infinite graphs. If you want to express things infinitely within a graph, which means that you are going to have an infinite set of either vertices or edges along the way, and again there you are going to come up with various other issues that are going to contradict with many theorems of graph theory. Yes, for edges, for example, here A to B is an edge, and A to F is an edge. So generally speaking, we consider these edges are to be finite for a simple graph. Well, when it goes to complex systems, like as I told you, the 6th degree of separation is quite a huge notions in which we can express it, but still we assume that that's going to be a finite limit that we have there. And that's again a small world problem. But if you really want to express something and we want to prove something using an infinite system, well, that's possible, but it's not up to this course to cover that part. We are going to just consider the simple graphs for our observation. Okay, let's look at some of the applications where these graphs are used. Can you think of some applications where the graphs are used? Well, for example, I have mentioned few applications of graph theory by beginning of this course, beginning of this lecture, as well as in some of the other courses. For example, even graph theories can be used in sociology. For example, the measure actors percentage prestige can also be explored. Or if you want to exploit other urban features, for example, if you want to consider each building within a town as a node, and the road that connects each building within a town as edges, in fact you are going to have a complex graph there. Apart from that, I have come across certain projects in which they are trying to see the location of old buildings within the town. And if you already know certain old buildings, like buildings which are more than 100 years old, so these are sparsely located within the town, and they have been marked as the nodes, and try to have a connections between these nodes. They are the edges. Why do we need this? Well, in case of an earthquake or other natural disaster, these old buildings are most likely to be disturbed. So we want to make sure that nothing happens during or after the disaster. In most cases, after the disaster, it is necessary to evaluate these buildings. Is it still in good shape? Well, for that, people uses graph theory based solutions to come up with. Well, that's one of the many applications that's there for graph theory. And in this course, after this lecture, we are going to have a series of lectures for graph theory, where we will also see different algorithms where it can be used to provide a simple solution. Two vertices A and B are adjacent or neighbors if the edge A, B is present. Okay, coming to this degree, an edge UV is incident on the vertex U and the vertex V. So, for example, the neighbor set n of V of vertex V is a set of vertices adjacent to it. For n of A is D and F, and then just for your information, this is supposed to be connected here. I think they are just out of, the line has just went out there between between D and C there. Okay, let's consider these edges, and if I suppose, let's look at this part, we will clearly see different features there. And from here I can clearly see that this particular edge, in fact it is not D and C, it is, yeah, it is D and C. Here again you can see it is C and D there. So degree of a vertex is the number of incident edges. So if you are asked to find the degree, you should just calculate the number of incident edges over there. Say for example, degree of D is the number of incident edges. For example, you have degree of A equals degree of B equals degree of C equals degree of E equals degree of F equals 2, whereas the degree of D is 4. The number of incident, whatever that hits the vertex. For example, vertex D here has been hit by 4 edges. As the degree of a vertex V is equal to the number of neighbors of V. So that's the question. Is the degree of a vertex V equals the number of neighbors of V? Well, that's one of the questions, but for multigraph it's no. So there are a lot of proofs that we have to develop. For simple graph, yes, it is. So the question again here, can you find these answers for this degree sequence? Is there a graph with the degree sequence 2, 2, 2? Yes, you can see here each node has two edges inserted on it. Each vertex has 2 edges. Yes, it is possible. And the next question is it possible that a graph with degree sequence 3, 3, 3, 3? Well, yes, it is possible to have such degree sequence. The next question is interesting. Is there a graph with a degree sequence 2, 2, 1? Well, you can think about or try to imagine this. Well, you can see this looks quite strange, which means that it is not possible to have a graph with a degree sequence 2, 2, 2. And again, yeah, that's the question, where does that edge goes? And is there a graph with a degree sequence 2, 2, 2, 2, 1, the similar one? No. So that's the thing that you can check about. You can ask about what's wrong with these questions or with these graphs. Handshaking lemma. So this is one of the simple lemmas that will help us to get more understanding of the simple graphs. For any graph, sum of degrees equals twice the number of edges. So the sum of degree equals twice the number of edges. In other words, it's always kind of even. Yes, twice the edges equals the sum of the degrees. For V is an element of V. A sum of degrees is an even number. The number of odd degree vertices even. Even if you have odd number of degree vertices, the number of odd degree vertices is also even. So that's like, for example, 2 plus 2 plus 1 is odd, so it is impossible to have such things. Again, the previous example we saw 2 plus 2 plus 2 plus 2 plus 1, that's it's still odd, so it's impossible for the actual handshake. So again, we can have simple proof of this. Each edge contributes 2 to the sum on the right, so that's one thing that we have, it's even. Given a degree sequence, if the sum of degree is even, is it true that there is a graph in which degree sequence, in such degree sequence? So that's one question that you can think about. Given a degree sequence, if a sum of degree is even, is it true that there is a graph with such a degree sequence? For a simple graph, no. Consider the degree sequence 3, 3, 3, 1. Can you try to come up with such a graph? For multigraph with the self loops, that's possible, it seems. So you can check it out, because we did by means of inductions. Well, now just we have seen a very simple outline for the basic graph theory, and still there are a lot of other things that are related to theorems of graph theory, on properties of graph theory. That's what we are going to look at in the next lecture. And moreover, the series of lectures that involves graph theory, we will also cover the actual applications and some of the algorithms that are used in graph theory, that is also used in many real world applications of modeling a real world system into a graph based model. So until I catch you in the next lecture, have a good time and see you there. Goodbye.